Hello guys, this is Prime Concept. Now I'm here again to unravel a very important concept in electricity. Now, from our previous videos, one of the topics we learned under electricity is the concept of Ohm's law. Now we can meet in circuit analysis. We would meet complex circuits where we cannot necessarily apply Ohm's law with ease. So there are other circuit laws that can help us analyze any kind of circuit. We have so many of them. In this video, I'll be handling one of them, all right? And that law we'll be handling today is what we know as Kirchhoff. Some people call it Kirchhoff, but I call it Kirchhoff. So Kirchhoff's law. So we'll be looking at Kirchhoff's law. This law was given by Gustav Kirchhoff, right? Now, and Kirchhoff's law is a law that we apply when we want to analyze complex circuits. Circuits where you have, let's say you have more than one voltage source. You can no longer directly apply Ohm's law to it. So you would need to use Kirchhoff's law and so many other circuit theorems. So Kirchhoff's law is divided into two parts. One of them is known as Kirchhoff current law or Kirchhoff junction rule. Then the other one is known as Kirchhoff voltage law or Kirchhoff loop rule. But we're going to start this way. There are terminologies that we need to understand so we can understand Kirchhoff's law. So I'm going to start by explaining the terms that are used in Kirchhoff's law, right? So the terms that are used, number one term we need to know before we dive into the law properly. Number one term you need to know is what we call junction. Junction. Now, of course, junction means literally the same thing you know in English, right? Now, what is a junction? A junction in a circuit is a point where three or more wires meet. Take note, a junction is a point in a circuit where three or more wires meet. It has to be three or more that makes a junction. Now, what do we mean? Say we have a circuit like this. We have a circuit like this. We have this. We have this. Still, we have a circuit like this. Now, you notice we have so many points in this circuit. This is one point. This is another point. So let's call this A. This is another point B. This is another point C, and so on. This is point D. This is point E, and this is point F. So if you observe this carefully, point A does not qualify to be called a junction. And the simple reason is because at point A, you have only two wires meeting at point A. So point A does not qualify to be called a junction. It has a name in circuit which I will still mention as the second term. But if we take a look at point B qualifies to be called a junction because you have 1, 2, and you have 3 wires meeting at point B. So in this circuit, point B is a junction. And if you come down, you'd also notice that point E qualifies to be called a junction because you have 1, 2, and 3 wires meeting at this point. So in this circuit, point B and point E are junctions, and obviously point B and E are the same junction. So they're going to give rise to the same values when you start analyzing this circuit. Now, what does point A, F, C, and D, what do we call them? So that brings us to the second term that is used, right? Which is what we call node. Node. So what is a node in a circuit? A node is a point where 2 or more wires meet. A node is a point where 2 or more wires meet. That is to say, this point qualifies to be called a node. So you have 1, you have 2. So this point is a node. This point is also a node. You have this, you have this. This is also a node. This is a node. Now, since we said a node is a point where 2 or more wires meet, it simply connotes that every junction is a node. Every junction is a node. So if I come back to this circuit, point A, B, C, D, E, and F, they are all nodes, right? So all junctions qualify to be called a node, but not all nodes qualify to be called a junction. I'm sure that concept is very clear. And the third thing we want to learn Number 3 is what we call loop. Loop, or you can still call it a mesh, but we'll be using the term loop more. So what is a loop? A loop is simply a closed path, or a path enclosed by circuit elements. A loop is a path enclosed by circuit element, right? That is what a loop is. So if you come here, you will notice that this whole place is enclosed by circuit elements, this and this. So this whole space you have inside here is called a loop. So this is a loop, right? Just like a circular path. You come here, this is also another what? Loop. So a loop is just a closed path enclosed by circuit elements. So we have, in this case, we have 2 loops in this circuit. So these are basic terms that we'll be meeting when we are studying Kirchhoff's law, and I believe that these things are very clear. So we're going to go straight stating Kirchhoff's law, and we'll learn how these laws can be applied in solving circuit problems, right? Thank you. So I'll rub this. So the first thing we want to study is Kirchhoff's first law. Remember I told you earlier that we have 2 laws that was given by Gustav Kirchhoff. So we want to look at first law, Kirchhoff's first law. Now Kirchhoff's first law is called Kirchhoff's current law. Current law, which for short you write it as KCL. So you call it Kirchhoff's current law, or another name you can call it is Kirchhoff's junction rule. The reason why you call it Kirchhoff's junction rule is because this law is applied at a junction. Is applied at a junction. Now what does the law say? The law simply states that the net sum of current entering a junction is equal to the net sum of current leaving the same junction. The total current entering a junction is equal to the total current leaving that same junction. What do we mean by this? Say we have something like this. Let's say these are wires connected and they are meeting at this point. Now we have a current here. Say this is I1. We have the current here. This is I2. We have a current here. This is I3. And we have a current here. This is I4. And say we have this. Obviously, you would agree with me that this point A, qualifies to be called a junction because you have 4 wires meeting here. Remember, a junction is a point in a circuit where 3 or more wires meet. So this point qualifies to be called a junction. Now, Kirchhoff's current law says that the net sum of current entering a junction should equal the net sum of current leaving the same junction. So let's derive the formula from this. Now, what are the currents entering, going into this junction? So if you watch, you'll notice that I2 is entering, is going to point A. So I'm going to write it. I2 is entering. Which other current is entering point A? You're correct. I3 is going to point A, right? You will see I3 going to point A. So I'm going to say plus I3. Now, do we have another current going to point A? Yes, you're right. Now we have I4. I4 is also approaching point A. So I'll also say plus I4. And the law says the total current entering a junction equals the total current leaving the same junction. So since I have all the currents entering, so I'm going to say equal to. Now, do we have any current leaving that junction? Yes, you are correct. And the value is what? I1. So I1 is leaving that junction. So I would say equal to I1. So what we have just written here is what we know as KCL, Kirchhoff current law, or Kirchhoff junction rule, which says that the net sum of current entering a junction equals the net sum of current that's leaving that junction. And we can still state this law in a different way. We can say that the net current at a junction is 0. So we can state this law the same way. The net current at a junction is 0. Reason being that I can rearrange this. I would write this simply as, if I bring this I1 to this side, it becomes minus I1, and this one remains, plus I2, then plus I3, then plus I4 equal to 0. So this is what the second way I have stated this law is saying, that the net sum of current at a junction equals 0. So in a simple way, we can simply generalize KCL by writing summation of current at a junction, say junction A, should be equal to what? 0. So what you have here is what we know as KCL. I believe this concept is very clear. I'll still give examples to help you understand this, right? Now let me rub this. One of the things you should also take note of, very important, is that KCL is actually a derivative, is actually a law that comes out from the law of conservation of charge. The reason is because KCL conserves charge. So it's a law that is derived from the law of conservation of charge. Thank you. Now let's take a simple example again. Now say I have a problem like this. I have 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 this. And this is R1, this is R2, this is R3. And then this current is I1, this one is I2, and this one is I3. So the question says, find the equation of current at junction A. So we have this, want to find the equation of current at junction A. So these are junction A. So to find the equation of current at junction A, we need to apply KCL. Very simple. Now what does KCL say? KCL says that the total current entering a junction equals the total current leaving the same junction. So let's watch. Which currents do we have going into this junction? If you watch closely, you would notice that I1, which is this, is actually going into that junction. So I have I1 is going into that junction. Do we have another current going into that junction? No, we don't have, because I2 is going out, I3 is going out, so we don't have another current. So I have I1 equal to the current leaving the junction. So one current that is leaving the junction is I2. So I would write I2 plus, do we have another current here? We have I3, so plus I3. So this is actually KCL at junction A. Now another way we can write this is our answer, but we can decide to still rearrange this to write it as I1. If I bring this to this side, I would have minus I2. I bring this to this side, I have minus I3, then I would say equal to 0. So any of these two equations is correct, right? I'll still give another simple problem so that the concept becomes clear to you. Now say we have this. Find the equation of current at junction A. Now say we have this diagram. We have this, we have this, we have this. Now this is I1, this is I2, this is I3, this is I4, this is I5, and this is I6. So we want to find the equation of current at junction A. We want to find the equation of current by KCL at junction A. It's very simple. So what we simply do is the sum of the current entering that junction. So let's get the current entering the junction. So the first current entering is I1, is going into that junction. I1, so I'm going to say I1 is going. Let's check which other current is entering. We have I4 is also entering that junction. So I would say plus I4. we have another current I5 going into that junction. So I'm going to say plus I5 entering that junction. So I don't think there's any other one entering. So I'm going to say equal to the current leaving that junction. So the first current leaving that junction, I'm going to say I2, because I2 is leaving, equal to I2 plus another current leaving is I3. So I'm going to say plus I3. Another current leaving is what? I6. So I'm going to say plus I6. So this is the equation, which I can still rewrite, bringing everything to one side. If I do that, I would have I1. I'll bring this to this side. It becomes, since it is crossing equality sign, it becomes minus I2. This is also crossing, it becomes minus I3. I4 is already there, is there, plus I4. I5 is already there, still plus I5, and then I6 will come. So I have minus I6, then equal to 0. So this is another way I can write this formula. And this is KCL applied at junction A. I believe the concept behind KCL is very clear to you. Let me restate KCL for you. KCL simply says that the total current entering a junction equals the total current leaving the same junction. That is KCL. Another thing you should also know is that KCL is a law that is derived from the law of conservation of charge, right? I believe this concept is very clear to you. I will be doing another video. In my next video, I will be explaining KVL, and then we'll be applying that to a real circuit and see how we can solve problems, find current in the circuit using KCL and KVL. In every circuit you want to analyze, you would always need to apply both KCL and KVL at the same time to be able to solve. So follow my videos and watch my videos, follow my channel so that you can get this concept on KCL and get it very clearly. Thanks for watching my videos. Remember, this is Prime Concept. Thank you.